Um,
launch
first of all,
recording and you have the mic open.
well, welcome back,
Thank you
everybody,
very much in
after the
advance.
summer. Um, the things have obviously been uh, getting interesting, but uh, what we were thinking of doing for this semester is taking taking a view of some of the objects and classes that are sort of integrative of the phenomena that we've been talking about. So the one that kind of gets everybody in at least the at least at the level of the funding agencies really excited is anything with the word origins in it. And since cosmology is kind of out of the reach of small telescopes, the other origin is either life or sort of the hotel that life is going to stay in. And that means star formation. And that was what we thought would be a good place to start. But I want to emphasize something that I'm not going to do the usual shtick of sort of starting with a cloud and having it go squish and then forming a star and then talking about the evolution. There's something much more basic here to ask if you were looking for something as young as a protostar, if you're actually considering the formation process as an observational question, what would you look for? What are the phenomena that you would expect to accompany the early history of a star? Now, for that, there are a couple of things that are important to emphasize. And I hope this will make sense. And if it doesn't, please interrupt, okay? As we've always agreed. The first thing to remember is that when a star is formed, it's not in the middle of nowhere. Um, its birthplace may be in the middle of nowhere as far as the galaxy is concerned, but stars in their formation are deeply embedded in a much more extensive environment. And that means a molecular cloud. Now, it's important to keep that in mind because that's also the bias for the discovery of these objects, that the way you look for them and the traditional way in which they were found, and consequently the way that the subclasses are also named, is they show up in regions that are heavily extinguished, that show large scale cloud structure, that have indications of dense interstellar gas, and most important, that show evidence for very massive stars in general. Now, in some regions like Taurus, you don't have the most massive stars, but this depends on the environment, and it's another one of those open questions that's remained unanswered now for a generation. But in general, if you see OB stars, you know bloody well that anything that you see with them in, say, the range of one solar mass is going to be a very young object and will not be on the main sequence. That is, it will be a star in a, sort of thermal equilibrium, sort of mechanical equilibrium, but one that has not yet settled down into the structure of core nuclear burning. Okay? This is really important because it means that the regions you're going to be looking at have something very strange going on with the presence of the massive stars and the low mass stars. The low mass stars are going to be more extended, that is, lower surface gravity for their mass than they would normally be in an ordinary cluster. Okay, so if you look at, say, the Hyades, you have one solar mass stars and you have zero point 0.8 solar mass stars and a couple that are expanded to 2 or 3 solar masses that are off the main sequence. But you don't have stars of one solar mass at, say, 3 or 4 solar radii. Okay, which means that the stars that you're looking at in the clusters that are associated with the very massive stars are already a bit strange and possibly fragile in the sense that the radiation that's coming from their massive companions is going to play a role in the evolution of their environments and may also affect their presence, that is, the formation of those stars. So the first thing is the place you look for these is kind of like the drunk under the lamppost. You look where the lighting is good, and in general, where there are massive stars. So, one of the traditional places that has been the site of discovery is Orion, since we know that this is one of the most active star forming regions in our part of the galaxy. But also Scosen, Camelopardalis. There are many individual regions scattered within a few kiloparsecs of the sun in which we know that star formation has happened recently. Okay? Now, that doesn't mean we're actually going to see the formation process. So let me make that second part clear, that the original class of star called a T Tauri star because it looked like T Tauri were and are stars that are on their way to stable nuclear burning. They're still in the process of contraction. They're still surrounded by extensive circumstellar material in general. They're lower surface gravity than a normal star of the same mass. And they're found in regions that are associated with dust and strong infrared emission. And that's basically it. The various classes of objects photometrically are different. That, as Francois said, the study of young stellar objects has largely been the purview of photometrists because they are faint, and they're faint in part because they're in these heavily extinguished regions. If you see stars that are young that aren't completely surrounded by dust, first, that would be very unusual. And second, it means that there's been some very strong interaction on the part of the massive stars to clean the environment out. So it's a very unusual region, and there aren't many of those. There aren't many cases of those. So even for regions like Orion, if you look at one solar mass stars, they're not going to be all that far above the main sequence, that they're going to be very much brighter. And they may be an order of magnitude lower surface gravity, but they're still going to be 10 or 12 or 14 magnitudes. So in general, studying these at high resolution in the optical has been a challenge and requires extremely large telescopes like VLT, Gemini, the Keck. And in general, not at very high spectral resolution, typically between 1,000 and 5,000. Now, I'll talk a little bit about those when we get to the spectra, but the other side of it is the discovery of variations in these stars was something already going back to the early days of photometry, that when you have stars in these embedded environments and you look at them in the optical, they show variations on all sorts of time scales, from regular variations on the order of days to irregular variability that can be anywhere from minutes to years. Some of it looks like flaring and is familiar from working on DME stars. Some of it looks like binary motion or eclipses, or, as we'll get to, rotational modulation. So, to sort of get things started, let me go to the screen share. So I hope you can see this. Yes? No? Okay, so um, what you actually, let me start with something even more basic. And I hope to be able to do this. If not, okay, this is going to have to be very primitive because it appears that the whiteboard isn't going to work. So let me start with a basic point. I said when you're looking at stars that are in their youngest stage, they're going to have surface gravities and physical conditions in their stellar envelopes that are different than they will have when they're finally in hydrostatic equilibrium and have ignited their core. Okay? So if you have a one solar mass or two solar mass star that's above the main sequence, it's going to be cooler for that mass than it will ultimately be when it's finally in equilibrium. Now, this has several consequences, the most important of which is the envelope is going to be convective. The surface gravity is lower in those, so these stars, among other things, whatever the other conditions are for these stars, are going to have chromospheres. And they may, because of their rotation and because of their convection, and this should sound familiar now because we've talked about this for other classes of stars, the stars will have the possibility of generating strong magnetic fields. That is, if you take a star like the sun and you evolve it off the main sequence, it's not the same thing as taking the star before the main sequence and evolving it forward. For one thing, you don't have the core nuclear processing. You also go through an intermediate stage where in these stars, because they have some residual deuterium, in other words, light hydrogen, they go through a stage of nuclear burning that lasts for only a matter of years. It's a very rapid process because it's the second stage of what the sun does. But because deuterium is such a small fraction of the abundance of hydrogen, it immediately disappears. On the other hand, you got this core that's gone through nuclear burning at low temperature for a short time, which leaves the outer layers of the star that adjust on much longer time scale in a real mess. That is, the object that was kind of a contracting ball, if you want to think of it that way, sort of bubbling away and slowly contracting as it loses energy, the suddenly becomes mixed. That it's gone through a turbulent process that doesn't settle down under normal conditions, that causes the star to puff up. It causes the mass loss to go up. It's something that, even though it lasts only a short time in the actual process in the core of the star, there's a very long delay in the decay of its effects because of the nature of the transfer of energy through the envelope of the star. Okay, so it's a little bit like striking a match and then making it a very strong match, a blowtorch, turning it off, leaving a room closed, and then looking at the way the room readjusts to the fact that that source was on for some time. Now, that stage changes the internal structure of the star in ways that really we still don't completely understand. But for one thing, the envelope is going to be strongly turbulent and strongly convective. And if the star is rotating, its rotation may be changed by this change in its structure. So, and maybe I'm getting a little bit ahead of things here. The this process of deuterium burning is one that you may have heard of in another context. It's the difference between a planet and a brown dwarf. That a brown dwarf is often called a failed star, but all that means is it can't process core hydrogen because the nuclear reactions require a higher temperature and a different density regime than those stars have because they're so low mass. Okay? But the important thing to remember is that in the nuclear process, the simplest of all, where you have two hydrogen nuclei smashing into each other, this process is a weak process. But if one of those, instead of being hydrogen, is deuterium, which has the same charge, but now has a neutron, the reaction is completely different. It goes as a normal nuclear reaction. It's a permitted reaction. And it is, in fact, the second reaction in the so-called proton-proton chain. But because it's really irrelevant as an energy production mechanism in a star like the sun, it's something that you traverse very quickly and leads only to the destruction of the deuterium. But when you have a protostar, the material hasn't yet been processed. So in the core, you have the deuterium that was residual in the interstellar medium at the time the star was formed. That deuterium is going to burn. Again, very briefly, it's only of order 10 parts per million of the abundance of hydrogen in the interstellar medium. But because the reaction is so much more efficient and has such a short time scale relative to proton plus proton, the amount of energy that it releases is substantial and leads then to this pulse of energy that comes out from the core, turns off. That is still an unknown, although there's lots of evidence that some of the residual rotation and binary properties of stars in this very young stage is inherited from the dynamics of the interstellar medium. But it's clear that stars rotate. I mean, let's just aside from the convection, let's get this point out so that it's just slowly contracting. That object has already got some spin angular momentum, whether it's in a binary or it's a single star. That is going to change over time in many different ways. And that's one of the things that's very important and central to the study of these stars. And that's the next thing I'm going to get to put things in context. The third is that I said the picture that we had when I was a child of star formation was that there's this kind of hiccup in a molecular cloud, and somewhere there's a little bit too much density, and everything just kind of accumulates there, and it can't support itself, and it collapses down, and that's it. Okay, you get this nice spherical star, and it just sits there and evolves. That's not true. For one thing, we know now that Francois' compatriot Laplace was actually right, at least part of it. And all star formation involves the formation of disks, whether they are accompanied by other stars that happen to form as very high mass ratio, that is, uh, low mass ratio, so that you have a number of objects, all of which are about the same mass, either a binary or a triple or a hierarchical system. Or you have a very high mass ratio of a central object surrounded by a planetary-like system or substellar objects. Regardless, the process of formation appears to be connected with disks. Now, in a sense, this is the most natural expectation, not just because of the Kant-Laplace nebular hypothesis and the fact that we had been looking for these things for a couple of hundred years, because looking at the solar system and the rings of Saturn and the distribution of the moon systems around the Jovian planets, you realize that you always have these planar configurations. So around these rotating objects, there's got to be something that aligns the angular momentum, aligns the rotation axes of whatever the environment is in which these objects are being formed and the rotation of the central object. So it was already considered that, yeah, disks are going to play a central role in the formation of stars. But before the 1960s or so, you didn't have a clue what they were going to look like. That is, what would be the signature if you look at a star that you say is a protostar because it's got all of the environmental links? What would be the signature of the presence of a disk? Okay, now you know that. It's called emission lines and specific forms of the emission and specific timescales. In other words, you can use your experience from binary stars and the accretion phenomena in cataclysmics like novae and dwarf novae, and what we talked about with active galactic nuclei, where you have extremely thick disks and massive dusty environments to inform what you would expect to see. That is, one of the signatures is going to be that you see a star, a stellar spectrum, with a very strong infrared excess, because it's going to have dust. It's going to be this is not the sort of accretion disk you get from a binary system. You'll see the emission lines from that too, because an accretion disk is an accretion disk. Okay? Doesn't matter how the matter is being supplied from the outside. Ultimately, the action in the disk is to get the matter from the outside in. Okay? Accretion is therefore a universal problem that involves the same physics, whether the source is from a companion in a binary system or it's coming from material in the interstellar medium or the material that was residual in the disk and that drifted inward to form the central object, which is where we stand now in trying to understand what's going on. But the key is whatever you have as the rotation of the star is, at least in part, a residual of that accretion process and the residual and the residue of the requirement that the material be supplied to the central object from a surrounding accretion disk. Consequently, it was expected that one of the things you would look for, besides a cold environment, and a cold environment also that had a temperature indicating the interaction with the central star, you would also think that the material that's falling onto the star is going to be coming not in the final stages slowly and quietly onto the star, but it's going to fall onto it. That if you can get the material close enough in the inner part of this disk, it should have a strong interaction with the underlying star. Now, again, we've talked about this sort of thing. It's what you find in cataclysmic variables when the inner object has a boundary layer, that the gas that has to come to rest on the stellar surface, because it is a star, because it can't be simply disrupted by the rotation, that material is going to have to slow down. The only way it can do that is by strong dissipation. With velocities of hundreds of kilometers per second, you would expect that there should be UV and X-ray emission. And if this sounds familiar, it bloody is. This is the same thing that you would see in Beta Lyrae, in W Serpentis, in any of the stars that are main sequence accretors in thick disks. Okay? So the study of a star like Beta Lyrae is a perfect analog to begin understanding protostellar disks. Okay, there's a difference in the amount of mass, and clearly in the earliest stage, which we can't see, we would expect that the circumstellar material is going to be self-gravitating. In other words, there's going to be enough mass that its own gravity is actually acting. And we don't really understand the turbulence. We don't really understand the magnetic fields involved. But what we do know is that from this disk, this strong dissipation that has to happen to get the stuff to drift in is also going to heat the disk locally. Okay? Again, if this sounds familiar, it is. This is the same thing we were saying, talking about Seyfert galaxies and dwarf novae and classical novae and mass exchange in binary systems. So I'll just keep emphasizing this for the rest of our discussion today. Everything that I'm going to be saying is applicable someplace else. And everything that you get from understanding the accretion phenomena in these other systems, and also outflow, as we're about to get to, immediately comes to mind for these systems as well. So now to go to the Okay, keynote, fine. So, okay, one of the things that is characteristic of these systems is that you see what are called inverse P Cygni profiles. You already know that when you have an outflow, the gas that is seen against an opaque surface or seen against a denser inner region is going to have either scattering or absorption that's displaced in velocity because it's flowing outward. If you reverse that, if you imagine now that you have the surface here and the material falling into it, then if you're looking this way, you would expect to see the map of the accelerated region now accelerating inward. So you would expect that you would see red shifted high velocity material rather than blue shifted high velocity material. And if you have variation in the accretion over time, those fluctuations should show up as a map of the material that's falling onto the central object. Okay? Now, this is what you would expect in the simplest picture, where you can imagine having the central star and say spherical accretion. But, and now I'm going to have to do this rather primitively, but imagine instead, can you see this? Okay,
Not well, no.
better?
Yes.
Okay, now you notice the way I've drawn the arrows. Imagine that material, instead of drifting inward or falling in spherically, is somehow channeled in its flow. We know this kind of flow from binary systems in cataclysmics. That is, we have cases, polars, AM Hercules stars, where you have a surrounding accretion disk and the central object, in that case, a white dwarf, has a strong magnetic field. That's internal to the object. So now imagine that you take a star that has strong convection. Remember, I said these stars have lower gravity, lower temperature, and low mass. They may, in fact, be more rapidly rotating because of the material that's been accumulating on them. So they're ideal sources for the picture we think governs the generation of magnetic fields by dynamos. Now, if you've got material that's falling onto that object, that material is not neutral. It's going to be ionized by the X-rays that are coming from the accretion and from the disk. And so that stuff is going to channel onto the poles. It's not going to simply drift in because the field is going to drape into and connect with the background. As the system rotates, the magnetic fields may show different aspects. That is, they may appear like that at different times and different angles relative to you as an observer. And so even at low resolution, because the velocities can be hundreds of kilometers per second, you'll see shifts. And those shifts should correlate with the rotation of the star. Now, in the realm of the photometrists, what's emerged over the decades is that young stellar objects look in their behavior very much like ARAS Canvan stars, which we've already talked about, that is strongly magnetized, synchronously rotating binaries with evolved stars. They look like DME stars, so flare stars, And and also the variations that are seen in W Ursa Majoris systems in contact binaries. That is, we definitely have evidence for star spots and also non-thermal radio emission and X-ray emission, and all of those varying on timescales that can be coordinated with the rotational velocity that's measured for the star. So what you're going to have in the accretion is an interaction between the stellar magnetic field, which must be there in these systems at different strengths, in different orientations, in different configurations, but they must be generating dynamo fields. And whether those are permanent or dissipate before the star gets to the main sequence is another question. But these fields are going to dominate the phenomena that you will see. So these are the sorts of behaviors that are seen
Uh,
in. Can,
Steve, just a minute. We
yeah.
don't see your
Um,
picture.
okay. Let me make sure that this is working. Um, Keynote, Wacom. Keynote. Okay. How's
Oh,
that?
good. Perfect.
Let me just make sure of one thing. Um, okay. Did you just see the screen?
Good. Yes, that's good.
Okay. So, um, the um, the lines that are usually used are in the red and the infrared. The Paschen lines are beyond most of your spectrographic capabilities, but the Balmer lines certainly aren't. Uh, and in these, you very frequently see asymmetric absorption, where the absorption actually is on the red side rather than the blue side, suggesting that the overall emission is coming from the disk environment and also perhaps from an outflowing wind, but that you see absorption redshifted because it's infalling. And it depends on which lines you're looking at. These are just a sample of the profiles from individual systems. The different profiles that you see uh, in typical astronomical fashion can be characterized by a kind of machine learning cartoon where the the different profiles are shown above, which are actually the same profile flipped around. So this would be one where you would think that you're seeing only an absorption or a strong column absorption. This is one where you would expect that you might be seeing an outflow. Something in the middle is completely ambiguous. And this is roughly the percentage of a class of T-Tauri objects based on the Paschen and the Balmer lines, just showing the relative proportion in these different types. And the key thing is which lines are showing which kind of profile is shown by the color. So what this is dominated by is infrared measurements. So the bracket gamma, the Paschen alpha and beta and gamma. And again, it's indicating that the environment is showing hydrogen emission, which means you got to have tenuous hot plasma, at least a chromosphere, if not a chromosphere plus an accretion disk plus a wind, and clearly some high optical depth material. Uh, Now, this is one of the systems, HQ tau. It's just from a relatively recent paper. The reason I'm showing this is that on the bottom left, you can see a light curve from TESS. On the top, there's the curve of the measurements of the circular polarization. That is, it The magnetic fields in these stars can be hundreds to thousands of Gauss. For comparison, for the sun, it's about one. Sunspots are typically of order of kilogauss, and when you see on a main sequence star a strong magnetic field, it's anywhere from 500 up. But these fields can be a couple hundred Gauss, and that's enough to split the lines and allow you to measure by circular polarization a a magnetic field strength. And the thing that shows up from these kinds of monitorings is that these stars rotate and the magnetic field is sort of kind of tied to the structure of the star. And the reason that you see the light curve, it isn't just the garbage around the star, it's actually star spots. Another indication is that these, on timescales of just a couple of days, can go through fairly large, like half a magnitude excursions or order of magnitude. Now, that may not sound like very much, but you're talking about 10 to 20 or 30% variations in the brightness of the object. Uh, that's significant when you consider how much area would be required to do something like that. These are the same kinds of phenomena that you're used to from DMEs, from flare stars. And you can also see that there's a modulation in this. So you simultaneously have flickering, short-term stuff, which is almost certainly an indication of the accretion, the variation by having pulsing, which is the flaring, the irregular stuff, and then the modulation from the rotation. The not to belabor the point, but in one recent study, in this case of H.M. Lupi, the picture that emerges is from comparing all of the available lines. And to put this in perspective, the velocities that are characteristic here are a couple of hundred kilometers per second. And the time scale for the variations is hours to days. So it is something that could be done with small telescopes at low resolution, like 1,000, with small spectrographs. The main thing being that you can spend time on it. What emerges from that is that different lines have different velocities and form at different places in the accretion column. This is the schematic of what I was talking about, that the picture that's emerged is that the inner portion of the disk, this inner boundary, is really an inner boundary, exactly the sort of thing that you see in AM Hercules stars, in polars, in cataclysmics, where the magnetic field prevents the accretion flow and the material heats up and swings through the field, going like a curtain onto the poles. In fact, it's referred to as an accretion curtain or an accretion column. The effect is that the material is actually falling into the star. And so there's a shock at the surface. This is the classical picture. And material is being funneled up toward the polar region. And this is going to show up as different lines with different velocities. The highest velocities, that is the highest redshifts, are going to be from the ones that are near the polar region. And as the star rotates, this is going to be modulated. Okay, now there's another class of stars among the very young objects called Herbig AE/BE stars. Um, Not because they look like Herbig, but in the same way that the T-Tauri stars were found in regions of star formation, the Herbig stars are also found in or near regions of star formation, except these guys are brighter and more massive. So these are the ones that are going to be the precursors of, say, Vega or more massive, while the T-Tauri stars are going to be precursors of the sun. One of the differences is that around these stars, you have circumstellar material. This is a deliberately primitive slide from 2006 that just shows a couple of examples of these objects where what's marked forbidden iron is really forbidden iron 2, and this is forbidden oxygen 1. And what this tells you, which you don't see in the T-Tauri stars, is that this is an environment that has material that's ionized, very low density. And again, this should sound bloody familiar because we talked about this in discussing the environments of luminous blue variables. This is an indication that you have line broadening, you have disks, but you also have material of low enough density and high enough temperature that it's ionized, and you're also seeing forbidden lines. So the variability, this will give you an idea of what the brightness of these objects is excessive. I mean, it can be a couple of magnitudes. The lines look very familiar in the sense that you've seen these in BE stars all the time. So it's an indication that you have emission regions and a relatively small covering factor relative to the central star. And you also see inverse P Cygni profiles and neutral hydrogen and helium and variability on all sorts of timescales. This was an indication also with very strong infrared excesses that what you're looking at is material that's accreting onto a central star and also circulating around the star. So the picture that has come out of all of this is so-called magnetospheric accretion. And leaving aside all of the details, the basic picture is that you've got the accretion disk, material turbulent and flowing in, tied to the magnetic field, except it can't penetrate into what would be the stellar Van Allen belts. And instead, exactly as you see on the Earth with the solar wind, the material falls onto the poles. There are also, because of the instabilities, material is falling in from the outside. You can get plasmons that are going to be ejected from this, that is, get little tying of the magnetic field that occasionally belches material out. And the picture then leads to something that looks like this, a calculation by Zhou and Stone using a three-dimensional hydrodynamics code. This is the sex and violence. The grid is here just for reference. And this is what one can do now as a way of simulating the accretion process on the disk. This is actually running the equivalent of a couple of days of the process. So just to run it one more time, the protostar is set up. You have the boundary layer here where the temperature can be a couple of 100,000 degrees. And then the rest of the disk is turbulent and circulating. You can see the structure of the disk in this cutaway. And there's also here the upper boundary of the disk, and the material that's falling onto the star can also lead to expulsion by jets, which is the last point, that these systems also show a class of phenomenon that was also discovered by Herbig and Aro. And so these are called Herbig-Aro objects. Uh, they're ionized regions. So let me see if I can stop this. Okay. These are ionized regions that can be a parsec across. There are a few hundred of them known now. They show velocities of 30 to 100 kilometers per second. They're strongly supersonic. They show forbidden lines and forbidden lines from fairly highly ionized and excited states. So there are shocks present, and these are expelled from the central star. Now, to make that point, this is one of those examples. This is a protostellar disk imaged with HST over a period of 5 years, showing the disk, the jet that's emerging from it, and physical changes in the jet. Now, this is all after the corrective optics, so this is real stuff. The scale up here is 200 AU. So this is roughly a fifth of the size of the standard disks that we can generally resolve. In addition, already known as an anomalous object for other reasons, in the 1990s, with an early observation with a coronagraph, so one that blocks out the central star, Beta Pictoris, which is actually an early type star, it's not a protostar, was found to be surrounded by a disk. Now, this also showed indications of discrete bodies that were falling onto the central object. The disk here is about 1,000 AU. The central object here is being blocked out. These are now the last part of the phenomenon. These are the so-called debris disks. This is the crap that's left over from the formation of the central star. This is no longer in the process of accreting onto the central object. This is the stuff that is going to be asteroid belts, comets, the Kuiper belt objects, and also harbor planetary and proto-planetary bodies. One example of a disk around one of these Herbig stars is AB Auriga, which this is the real thing. That this is not the model that you were seeing from the Princeton group. This is of order couple of hundred AU across. It's verified by a STIS coronagraph observation, and this is the material with gas and dust that's circulating around the central star. This is what's responsible for those emission lines. Now, you won't be able to resolve this. This takes very high resolution and VLT, or STIS, which has the HST resolution of less than a tenth of an arc second. But the lines that are formed in this, you're going to be able to see. These are changes in one of these systems over time. AU Mike is also, oddly enough, one of the most active flare stars that we know. And this also is a system that harbors several planets. So in addition to the gas and the dust and the debris, you also have planetary bodies that can change this, and that affects the light curves. Finally, this, I have to see if I can do a full screen here. Let's see, possibly this way. Okay, This is an NTT observation that's rather old now. It's about 20 years old of one of these Herbig-Auro objects that is a jet emerging from a dark cloud. Um, when ARAS was launched in the 1980s, when some of the principal infrared observations were begun in the 80s and 90s, this was the Holy Grail. That is, to actually see the birth of a star. JWST is actually capable of penetrating what here is optically thick because of the extinction in the optical. Because HST can go out beyond 1 micron and actually see through this. But this is an object that is in the protostellar phase. Okay? This is another example of one of these jets where the working surface is going out into the interstellar medium. You've seen this coming out of chimneys. Well, maybe not because this is supersonic and it's ionized. And if you've seen that, you should be careful. But you can see the individual pulses. You see that this is something that's not steady. This is the evidence that you have outflows being generated from the disks and from the accretion process and from the magnetic fields. So everything that you might be able to study with the variations of the lines will then give you the information about what's going on in this deep, dark region in the inner boundary of the jet and the inner boundary of the accretion disk. So, I apologize for how broken up this has been, but I hope it's made some sense. As things you can do if you get interested in this, the principle is photometry. This is not very well covered, but it's one of those areas that has gotten active interest over the years. The key difficulty with this is that because most of the variability is going to be really noisy, it's really got to be followed carefully. That is, when you have random processes and and these are modulated by structure, like the magnetic fields or like the disks, you have to be very careful about the way you're sampling. You've got to have both very high cadence and long term. And those are precisely what you don't have in most time series in general that we've talked about. But it's worth doing. I haven't mentioned that within these structures of the disks, because they're dusty and you have debris that can obscure the central object, you also go through occultation events that almost look like eclipses, but are really just that you have the equivalent of large pizzas that happen to obscure the central star every once in a while that aren't planets, but they're large enough bodies that you can actually see the structure change over time. Uh, the other is that within the disks, the example that you saw from the resolved AB Auriga image, you actually have large scale structures, rings and spirals that are the result of the material circulating around the central object at orbital speeds. For spectroscopy, virtually any monitoring that you could do would be interesting. Several of these stars are actually rather bright. For the Herbig stars, many of them are HD objects, which means they're going to be brighter than 11th or 10th magnitude. And many of them, in fact, are also in the MWC catalog, so they're about as bright as symbiotic stars. And they're worth doing. Uh, you might not be able to do the radial velocities, at least at the level of orbits, but you can certainly look for changes in the line profile. And the main thing is that the the frequent monitoring of these objects and and being involved perhaps even in campaigns that are being organized will be very important. And I'll add two other things. Uh, they're neat because they're unpredictable. So you never know quite when you wake up in the morning what your data set is going to show you. But more than that, you're looking at one of the more complex objects, more complex stages of stellar evolution that requires everything that we've already talked about to understand. So, in one sense, these are exotic objects. In another, they're exotic because they have all of these other prosaic phenomena that we've understood or are understanding from all of the other objects we've been talking about over this last year. Then you can apply all of that accumulated experience to the study of these objects. So I hope at least this has put something in perspective. Getting into all of the other details of how the disk evolves, how the magnetic field interacts with the disk, what the turbulence is, what the origin of the winds are. All I'll say is in each one of these cases, just change the name of the object to an accreting binary that is a cataclysmic variable, a magnetic star, a rapidly rotating star, a luminous blue variable, or nova, or dwarf nova, or as a Seyfert type 1 or type 2. And many of the things that we've been talking about will already have been explained. So, see that I've been talking for too long already. So, if there are any questions, let me know now or later.
Yes, I think there was a question was by Michael Poxon. Do you want to take the micro, Michael?
Ah, sorry. I yes, I actually thought the questions were by text only, which is why I put it in chat. No, from what you were saying about dumping on the pearls of material, um, I know of at least one YSO. This is V1331 Cygni that's actually pulled onto us, but we don't see very much photometric variation. Just wondering why that might be.
Well, if it's pull on, then you're not going to see modulation, right? So what you would expect is the changes in the accretion rate might give you fluctuations, but the the real the real problem is that you don't have velocity resolution because when you're looking down on the pole, that also means you're looking down on the circumstellar environment, right?
Yeah.
So the material that's funneling onto that is potentially going to be varying, but you're going to see that only when the accretion rate varies. Okay, you're not going to see line profile variations, and you're going to see only a small area rather than the whole accretion column. And also, if it's pole on, you're not seeing the other pole.
Right. No, I was just thinking about in the circumstellar material being funneled onto the pearl.
Yeah, but that's falling in, right? Where you're going to see it will depend on where the line is formed, but most of those are going to be formed near the stellar surface, not in the whole column. So the only reason I would expect that you would see the lines varying is if the accretion rate is varying.
Ah, yes. I'm talking purely about photometric variation here.
And you see, that's the other point because it's a very small area.
So there's not much area to affect, so you're not going to see a lot of variation.
And also, and maybe this is more to the point, the problem is the kind of filters here that one uses. If you're using narrow filters, then the contribution of the emission lines, which are going to be more responsible for what you're seeing in, say, the optical variations, like H alpha fluctuating, those are going to be very small fractions of the total emissivity. If
Right. I'm actually using twin organic detectors, commonly known as eyes.
Okay, but the other is that you're not seeing variations of the disk against itself. You're looking down on the disk,
Yeah.
so uh, you have there's no self-absorption. You have a much larger area, much larger projected emitting area. So it if you actually the easiest way of saying this is you can imagine that you've got the disk seen face on with variability of the sort that you saw from the simulation by the Princeton group, except you're looking down at it. In addition to which, you also have a wind coming out. The region is going to be varying. Every portion of the disk is going to be varying on different timescales.
Yeah.
In fact, that noise can very easily wash things out, that you don't have a single region that's dominating.
Yeah, that makes sense. Yeah.
Also, the structure that you see in these disks is that they flare. And so when you're looking down on them, you're not seeing any of that effect. There's no self.
Yeah, you're not seeing the flaring region, are you?
So
Yeah.
I mean, it's an interesting point that, on the other hand, in this case, you would have I would expect in the X-rays, you would be able to see enormous flaring and enormous variability because that's going to be much more sensitive to what's going on in the shock.
Yeah. That's a great and a very full answer. Thank you very much.
Well, thanks. There isn't enough done in these objects, frankly. Uh, they are faint, but uh, they're a lot more interesting than dwarf stars. Um, they they do vary on very many. Sorry, they vary on very different time scales, and because they have multiply contributing regions, your experience or your background in, say, cataclysmic variables, and specifically the AM Hercules stars, which are accreting systems with magnetic fields, is you can use all of that experience to understand these systems. And in those cases, it would again be the case that if you were looking down on the system, you wouldn't see what you're going to see if you're able to get the whole accreting region. That is, if you're looking at, say, line profiles formed from the side.
Okay, Bob?
Thank you. Steve, since you mentioned that these are more exciting than dwarf stars and that they're varying on a lot of timescales, you may know some of us have organized photometry and spectroscopy campaigns on dwarf flare stars, and they really are pretty exciting. You know, you sit on the star all night taking photometry at maybe a 1 minute cadence and spectra every 5 minutes. And over the course of a week or a month, you see a lot of these events, and hardly any professional observatory can schedule that kind of time.
Yes.
Would there be a few of these objects that it might be fruitful to squander a few months of observing time that way?
Absolutely.
Any
Uh,
favorites in your mind?
uh,
10th or 11th magnitude, we can
Actually,
do.
one of them, unfortunately, is in the southern hemisphere, AU Mike,
Oh yeah, too far south for us.
which in I think some circles is called Speedy Mike. It has a very high rotational velocity. It's one of the most active flare stars in the sky. It also has a protoplanetary system and a debris disk. Uh, so systems like that that are known active stars that are sitting inside debris disks would be interesting to do. Uh, the ones that I think are the most interesting are always in Orion, but I have this strong prejudice for that part of the world. Um, but among the other systems, the ones that show massive outbursts and where the disk actually outshines the central object are called FU Orionis objects or FUORs. Uh, those are a class of object worth monitoring. I'll put it differently. Any of these are worth monitoring, especially those that have indications like uh, some of the Taurus objects of active jets, some of the ones that I was showing you, where you can see the central object. You know that the jets go through time evolution and you're seeing blobs that are moving out. I mean, all of the experience that you would have from the changes in the structure of radio galaxy jets shows up here, except these aren't relativistic, but they do vary on timescales of years or months. And the correlation of the appearance of these structures, which are going to show up in the high resolution monitoring with the photometry, can be very valuable because there are people who are going to do the occasional spot imaging. I didn't show the example, uh, but just to go back for one moment to a screen share, the so RY Tauri is is one of these T Tauri stars. These are 7 epoch observations done at high resolution, where this is an offset of a few arc seconds. So you're not going to see this, right? But these are blobs that spectroscopically, because this is done as a data cube, are like 200 kilometers per second. And this is covering a period of, well, you can see here, this is covering a period of roughly 10 years. So knowing something about the photometric history of this object during that period might allow you to correlate the injection events, or rather the ejection events, when something might have happened on the star or in the disk that would have provoked some large scale structural change in the jet. Now, most of these are not going to be monitored on that scale because they're not going to go, they may not show transient behavior of the sort that would trigger, say, any of the transients searches. Now, some of these are going to show up, probably many of them are going to show up when doing the photometry from the LSST, but they're not going to be standout. And they're just going to be varying like noise, and probably they're going to be filtered out of some of these large scale surveys. Certainly, if you're looking for transients, these are not going to qualify because they won't show that kind of amplitude that will trigger what would be a nova alert or a dwarf nova outburst or something like that. Yeah, these would very, very likely be worth monitoring.
Well, the RY Tari is kind of attractive because it's bright. Francois is 9.3 VMAG, so it's well within the range of our spectra for
Yes.
resolutions of maybe 2000 or so.
Yes, I completely agree. Um, the some of the objects in the Taurus cloud are actually quite bright. I mean, above 10th magnitude.
Mhm,
So very easily accessible with something like ALPI or even the low resolution of LIRES.
mhm.
Yeah,
Great.
also,
Thank you.
probably also worth pointing out that AB Origi is between 7th and 8th magnitude visual, so that's even brighter.
AB Auriga is one of the neatest stars I know. Among other things, it's the this is like walking down memory lane. One of the earliest UV observations I was ever involved with was taking high resolution spectra with IUE, which was a 40 a 45 centimeter telescope um, at carbon 4, and this thing shows what looks like a P Cygni profile at like um, 800 kilometers per second, except that it's a B star. Okay, so this is not your normal object. It's clear this has a strong wind. It's got a debris disk. We know from the UV that it varies, and so it would be very interesting to monitor that periodically to see things like the variation of the permitted versus the forbidden lines, because they're going to be coming from different density regions and might, well, will give you information about the accretion process and the outflows.
Plus, it has a low mass traveling companion in SU Origi as well.
Hmm.
I
Hmm.
think I think they have a common proper motion. I'm not sure how close they are.
Well, AB also has at least one planet. So most of the interest in these systems comes from the disks, and much of that comes from the presence of structures in the disk that indicate interaction with a massive body embedded in the disk. So resonances and gaps and small vortex-like structures that show up in many of these disks. In fact, there's the gallery. Um, just as an example, this is from ALMA. So this is the dust emission from a whole boatload of these, and you know they're rings, meaning that you have concentration of the material in, say, toroid-like structures. Not all of them show only one. Some of them show multiple rings, like fomalhaut. Uh, they're all of these are worth looking at over over a period of time, even if it's just, say, high cadence over a couple of weeks and then going on to another object and returning to these over some interval of time to see whether changes occur.
Uh, Steve, can I just say it's actually my birthday today, and this is one of the best presents I've ever had. It's an absolutely brilliant talk. Thank you.
I'm 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 I'm, I'm
Okay,
um wow,
I'll shut up now.
thank you. Um, I hope it's clear how delighted I am to be able to be with all of you guys. Um, this is something very special, and I look forward to our being able to continue them. And happy birthday. You made it through another, huh? I have a card that I keep over my dog's dish, which is one that a friend sent many years ago, that statistics show that people who have more birthdays live longer.
Okay. Any other question for Steve or no? So thank you very much, Steve. And I recall that the next session in October will be about B stars.
which will be sort of the next in line for um, systems that show virtually the same phenomena.
Yeah.
I think that's let's put it this way. The theme this semester is going to be everything about these weird objects you already know. It's just you know it by another name.
Okay.
So
Thank you very much,
see
Steve.
you all soon and have a good weekend.
Thank you very much to all and see you. I stopped the recording.